If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. So far, we've talked about the McCulloch Pitts neurons, and we've also talked about the perceptron. So in this tutorial, we're going to cover the geometrical interpretation of McCulloch Pitts neuron as well as the perceptron. Please understand these are the foundational videos for deep learning. So if you have a good grip right from this stage, you will find it a lot easier as we progress through the course. Let's understand this a little better. So far in McCulloch Pitts neurons, the condition was that the inputs and output could only be attaining values like 0 and 1, nothing in between. It could either be 0 or 1. And we could have a combination of these depending on the situation we are looking at. Now, if the sum of all the inputs added up exceeded a certain threshold theta, is when we used to say that the output will be 1, otherwise it would remain 0. And as a result of the restrictions on the inputs being zeros and ones only, the choices of theta were also restricted. So let's take an example of only two inputs in this case, x1 and x2. If both are 0, then x1 plus x2 would be 0. Let's say the outcome in that case is given to us as 0. Similarly, if one of these attains a value 1 and the other is 0, in this case or in this case, the sum of x1 plus x2 would be 1, and we can call theta as 1. And let's say in that case, the output is also given to us as 1. And in the last case, let's look at x1 and x2 both attaining the value of 1. Obviously, x1 plus x2 in that case will be 2. That's theta. And let's say the outcome in that case also is 1. So we are talking about an output that's already given to us. Now, if you know the logical gates, you know this is the example of an OR gate. If any one value is 1, the output is 1. If both are zeros, then the output is 0. Let's see how does it look like when we try to interpret it geometrically. And would there be some limitations associated with it? That's also what we'll try to understand. Okay, let's look at the interpretation of this scenario. We have 4 points. First is the origin, which is 0, 0. Then we have 1, 0. We have 0, 1. And we have 1, 1. You can imagine in all these cases, for these 2 points, which are marked in green, as well as this point, the outcome is 1. Why? Because we are saying x1 plus x2 is greater than or equal to 1 here. x1 plus x2 is greater than or equal to 1 here. As well as this case, both are 1, so the total is 2. You're able to do a classification in this case. Anything which is below this line is supposed to be a different class, which will be, let's say, represented by the red color, because we talked about a greater than or equal to sign in the decision function. So anything which is on this line or above this line would be classified as green. So we are able to achieve what we want to achieve at the end of it, right? Let's say if we change this value of theta to 0, now you can see at this stage we are doing one misclassification. Because as per the model, this region on or above this line is all supposed to be greens. But we have one point which is actually in the original data labeled as a 0. So this point is misclassified. Rest of the points are properly classified if we change the value of theta. If we change the value of theta to 2 on the other hand, we are again doing some misclassification because right now the only point that's being identified as 1 is this point. And the points which were satisfying the condition of greater than or equal to 1 are no longer being identified properly. So we can only adjust the value of theta here in case of McCulloch Pitts neurons and nothing else. And that's why our controls are rather limited. This would be a line with a certain slope, and that's how it will remain because we are simply saying the equation of this line is x1 plus x2 is equal to theta. So the first thing is that it's trying to classify using a line, and it has limited choices in terms of adjustments. It can only be shifted upwards or downwards because the only factor that we can control is this theta and nothing else. That's the limitation of the McCulloch Pitts neuron. Now let's talk about the perceptron. Just to refresh the understanding, perceptrons could take real inputs, and we also introduced the concept of weights here. So the expression here is wi xi added up should be greater than or equal to theta. Then it will be 1, otherwise it will be 0. And of course, as a result of these xi's being free to attain real values, and these weights also as some real values, the choices of theta were no longer restricted. You can imagine it through this table. Let's say we take x1 and x2 as not only zeros and ones now, but some real values, 0.1 and 0.2, 0.2 and 0.5. Depending on the choices of weights, you can calculate the values of theta. And here are the outcomes that are already given to us, right? So let's try to see how would this look like geometrically. So let's gradually make the transition. To begin with, let's assume that even now with this perceptron model, we are only considering the inputs which are like 0, 0, 0, 1, 1, 0, and 1, 1. How would this line be affected as a result of the fact that we have now introduced some weights and biases, right? So we can adjust these weights. For example, let's say I try to alter the value of W1. Do you see the line changes its slope a little bit? And accordingly, if we change the value of W2, you can see if we go here, everything is called red. Of course, we are doing more misclassification. If I shift it more to the right, it's doing a little better, but we can also adjust the bias. So we are no longer restricted to the limited choices of W1s and W2s because these can attain real values now. And accordingly, we can actually improvise our classification ability. We can adjust these values depending on how it would look better. And we may, over a period of time, see that we are able to do a better classification. For example, right now, if you see somewhere in between, if we try to settle this, we are kind of almost there. We are able to do a classification properly now. Anything which is on or above this line is green. Anything below is red. And we are able to achieve the classification. So essentially, the perceptron model brought flexibility. We could adjust the slopes of the line, and we've taken some restricted values here. Otherwise, if you're free to learn, you can try other options as well. For example, this is also a valid solution. I can move this a little further. So it gave you multiple solutions because your values were no longer restricted to be constants. As of now, we are looking at x1 and x2 as 0 and 1 only. But even if these were real values, owing to the fact that you can change W1 and W2 and bias, you can get multiple solutions. And of course, we can accordingly alter the value of theta as well. Now let's try to see if we no longer look at these points as only zeros and ones, but we look at some real values as we kind of showed you in the grid on the slides. Let's look at that example. So as you can see now, we no longer have the inputs restricted to zeros and ones. We have the first point, which is 0.1, 0.2. The second point is approximately 0.2, 0.5. Third point is 0.4, 0.3. And this is 0.7, 0.8. These are the coordinates. You no longer have values at only 0, 0, 0, 1, 1, 0, and 1, 1. In that case, again, we can adjust the values of weights and biases and obtain different results. And of course, we can also attain more realistic values for theta. Because the values of x1 and x2 are real inputs now, when you clump them with the real values of weights and biases in that expression, you will be able to attain a wider range of values for theta as well, right? So we may want to balance it. We may want to keep on changing it to see if we get better results. For example, even right now, what we see is a valid solution. All the green points that we had here, which were supposed to be identified as ones, have been identified on one side by the model, and all the red points, just one red point that we had, has been identified properly. We can further look at more solutions. We can adjust the value of bias, and this is more of a borderline case. On and above this line is green, and below this is red, right? We can adjust the values of weights also and see if that gives a better solution. So probably this is not a good solution. Maybe we shift it to the right and maybe a little further to the right, and that will be a better solution. So goes for the weights of W2. This is making some error. This point is misclassified. So we realize that going leftwards is not the right solution. We can go rightwards, and it'll continue to give us better solutions. So we just, for demonstration purposes, took some range of values for W1 and W2. We've not yet talked about the learning process, as we'll figure out. So essentially, if we sum up whatever we've discussed so far, we realize that both McCulloch Pitts neurons and perceptrons use a linear separator. They rely on the equation of a line. The line becomes more flexible, can serve a larger variety in case of perceptrons, which was very restricted in the case of McCulloch Pitts neuron. But before we end this video, just some food for thought. There could still be some cases where these points are not linearly separable to begin with. No matter what you do, you cannot correctly classify with the help of a line. And what could that scenario be? Let's look at that example. So we've made a slight change here. What we've done is this one more point, which was green here, we've converted it into a red point, which means this is 0 and this is 0 in terms of its actual class. And these 2 points represent ones. Now, no matter what you try as adjustment here, whether you try to change the value of theta, you try to alter the values of weights, you try to alter the values of B, no matter what combination you try, you will not be able to find a single line that separates these points into zeros and ones properly. So the point is, not every problem in the real world that we deal with is about a linear separation. It is quite likely that the points to begin with do not have a linear separation possible. And in that case, of course, the perceptron as well as the McCulloch Pitts neurons would fail, which is the kind of example that you're looking at. So we'll see more on this, why we always talk about nonlinearity when we try to apply deep learning. This is where that motivation triggers from. Also, we'll revisit one more major opportunity with perceptrons in the next tutorial.